Welcome to More Learn, More Teach, where I attempt to simplify the complex. Hello. Today we're going to talk about redox reactions or oxidation reduction reactions. You could say reduction oxidation reactions, redox. In a redox reaction, we're typically talking about ionic bonding, okay? And in an ionic bond, one atom will give up an electron to another atom. Okay, so the atom that gives up the electron is said to have been oxidized. The atom that receives the electron is said to have been reduced. Okay, so here's an example. We have lithium-7. Lithium-7 has 7 protons. Because I have 7 protons, I have 3 electrons. Starting from the lowest energy to higher energy, we have 2 in the 1s shell and 1 in the 2s shell. So the valence electron, the valence shell for this lithium-7 has 1 electron in it, and it is in the 2s shell. Fluorine-19 has 9 protons. Because I have 9 protons, we have 9 electrons to make it neutral. Starting at the bottom and working our way up, we have 2 in the 1s, 2 in the 2s, but we only have 5 in the 2p shell of the fluorine. So to have a full valence shell, the fluorine would have to have another electron. So I have an extra 1 in the lithium, and I'm missing 1 in the fluorine. So atoms want to have a full valence shell. Full shell being defined as either a completed S shell or both a completed S shell and a completed P shell. There are always exceptions, but in general, this is what they try to do, and that kind of tells you how reactive a substance is. So lithium really wants to give away this 1 electron because it's kind of unbalanced, right? It's got this this full shell here. The only thing that's making it unhappy is this extra electron it's got. But if it didn't have this extra electron, then it would have a charge on it, and it doesn't want to just have that charge. So this electron exists. This fluorine would love to have an extra electron. However, there's only 9 protons. If it had an extra electron, it would be charged, right? So if it just existed in nature, assuming that it was not bonded to something else, that's what we would have. All right, so if I combine the lithium and the fluorine together, right? If I have some kinetic energy, I have this lithium, I have this fluorine, put them together, then there's a statistical probability, pretty high statistical probability, that this electron will be stripped away from the lithium and given to the fluorine. When this happens, this lithium and this fluorine become ionically bonded. So the ion moved from the lithium to the fluorine. The lithium was oxidized. The fluorine was reduced. This will become lithium fluoride. So if I combine these together, this becomes lithium fluoride. All right, so now that we've talked a little bit about ionic bonding, let's talk about these rules for oxidation reduction problems. Okay, so the oxidation number concept is kind of like a bookkeeping and accounting that chemists use in order to help balance equations, right? So there's several rules to make this bookkeeping exercise work for us. So in general, if there's no ion, so it's a neutrally charged molecule or atom or whatever, then it's going to sum to 0, right? So all of its parts are going to sum to 0. If it is an ion, then the sum of its parts are going to add up to whatever the ionic charge is, okay, for that compound or ion, okay? If I look at a periodic table, look at the left and right side, okay? In general, right, the alkalis are going to be a +1. Makes sense. They have a electron configuration and the valence electron of S1. Okay, so in general, it's going to have an extra electron it's willing to give up. So it's going to be a +1. The alkali earth metals are not as reactive, but they do find themselves in several amount of compounds. So they are useful to know that in general they're going to be a +2, right? Because I'm going to have 2, although it is the S2, sometimes they're willing to give up their whole the whole S2 orbital in order to be happy. Okay, so they have a +2. On this side, we have the noble gases. Noble gases are generally non-reactive, so we don't really talk about them in these equations. However, under certain conditions, they do weird things. The other rules would apply to modify what the noble gases would be. Same kind of principle we're going to do with the metals. We're going to ignore those because they're going to respond to whatever else is going on. Right? We're going to look at the other rules and see how they apply to the metals. Okay. All right. The halogens are going to be special here. We're going to have fluorine is always going to be -1. However, chlorine, bromine, and iodine are going to be special. So it's going to be -1 in general. However, if it's combined with oxygen or fluorine, then it's going to be something different, right? So the rules of oxygen and fluorine are going to dominate if I have chlorine, bromine, or iodine with the oxygen or the fluorine, okay? So fluorine's always going to be -1, which means that if I have some chlorine, bromine, or iodine in there, it's going to adjust accordingly in order to make fluorine -1. Oxygen. Oxygen special. It's in general going to be -2. However, if it's in a peroxide, then it's going to be -1. And if it's with fluorine, then the fluorine's going to dominate, and the oxygen is going to be +1. Okay, so if oxygen's combined with fluorine, then the oxygen will be +1 for its oxidation number. Hydrogen's another interesting one, right? So hydrogen is going to be +1 in general, unless it's combined with a metal of some sort. If it's one of these metals, then it's going to be a -1. All right, so those are the general rules. And now we will apply these rules to some applications. Our first example, we're going to combine chlorine gas with sodium bromide, it's a powder, to form sodium chloride, again, powder, plus bromine gas. Okay, so if I look at this reaction, I start off with chlorine gas. It is neutral by itself, therefore it has a oxidation number of 0. So we start off with 0. Sodium bromide together must be 0, since sodium is an alkali and bromine is a halogen. We're going to end up with +1 and -1. We didn't have any of the exceptions here, so that's just going to be -1. So +1 for the sodium and -1 oxidation number for the bromine portion of this. When the reaction happens, we end up with sodium chloride. Again, I have sodium, which is the alkaline, and chlorine, which is the halogen. It doesn't have any of the exception rules, so it's -1 and +1. Okay, so the sodium is +1 and the chlorine is -1. The bromine is now by itself, bromine gas, so therefore the oxidation number of this has to be 0. Since we had a change happen, we have a change of oxidation numbers, therefore we have a oxidation reduction reaction, a redox. Okay? So what happened here? the chlorine was reduced from an oxidation number of 0 to an oxidation number of -1, which means that it gained an electron, right? Reduction is gaining of electrons. So we're going to gain an electron here, and that's what we did, right? So from chlorine by itself, over here, we now have a -1, right? It gained an electron. The chlorine gained an electron from the sodium in this compound, which gives us this -1. So the chlorine was reduced from 0 to -1 oxidation number. The sodium was unchanged from one reaction to the other. And the bromine was oxidized. It went from having an extra electron to being neutral again. So it was oxidized. So it lost an electron to get us from -1 oxidation number to 0. All right, quick note about the sodium. So as we pointed out, the sodium was unchanged oxidation number from this side of the reaction to this side of the reaction. I do want to kind of point out, I know that it was a struggle for me to understand when I was first learning chemistry. These are equilibrium states to equilibrium states. So you are not seeing any of the explosive reactions that might be occurring from one side to the other. So what's really happening here is this chlorine gas is combining with this sodium bromide, stripping out the sodium and the bromine. It's this reaction's occurring. It might be exothermic. I'm not sure in this reaction, but energy is exchanged in order for this to happen. When it's all said and done, this is what's left. Okay, so yes, it's true that the sodium had the same oxidation number from here to here, but in the process of going from here to here, the sodium might have undergone many different occasions, right? Or many different transformations. And this sodium is not necessarily exactly the same as that sodium, right? If it was sodium 1 and sodium 2, they may not be the same, right? Because again, these are averages. These are equilibrium states from here to here, and these are going to be statistical sample sizes, right? So large numbers of them. It's not a single sodium becomes a single sodium over here. It is a bunch of chlorine, a bunch of sodium bromide combines with a bunch of to create a bunch of sodium chloride and sodium bromide. All right, let's do one more example. Let's do a lead acid battery. Okay, so we're going to describe what happens when you are discharging a battery. So here we have a plate that is lead oxide. We have a plate that is lead, and it is sitting in a bath of sulfuric acid. Over time, it will discharge into lead sulfate sludge and water. All right, so if we look at the oxidation numbers that we have present here, using our rule for oxygen, oxygen has a oxidation number of -2. There are 2 of them, so therefore, in order for this to balance and the whole thing to be 0, the lead must have an oxidation number of +4. Okay, so -2, I have 2 of them, that is -4, therefore this must be +4 in order to make this balance. Okay, the rule for hydrogen, in this case, hydrogen will be +1. I have 2 of them in each molecule of sulfuric acid. I have 2 in the equation in order to make this this balance. Therefore, I have 2 times 2 times the oxidation number of +1. Using the rule for oxygen, I have -2 for the oxidation number. There are 4 of these for each molecule. There are 2 molecules. Therefore, I have 2 times 4 times -2. That would be -16. Taking what I have for hydrogen, what I have for oxygen, making this balance gives me what I have for sulfur. Okay, for sulfur, I'll end up with 6. So my oxidation number is going to be +6. Again, I'm going to have 1 for every sulfuric acid, but I will have 2 molecules for this equation. Okay, but the important thing out of this is the oxidation number. The oxidation number is +6. Lead by itself is going to be 0, right? Because it's got to be balanced. So this is what we start with. As the battery discharges, we end up with this. Nothing changed here in the oxygen and the hydrogen, right? So the oxygen rule is still -2. Okay, so I've got 2 of them because there's 2 molecules of water. So I have not changed the oxidation number of oxygen. I also have not changed the oxidation number of hydrogen. Again, I have 2 times 2, or 2 times 2. Oxidation number is still 1. This balances, right? Because this is 4 plus, this is 4 minus. It all works out. My sulfate didn't change. This is the same as it was over here. None of the rules changed. Okay, so we have a situation where we have lead and we have sulfur. Both of those have rules that depend on other rules. However, this sulfate is a molecule in and of itself. It stayed the same from here to here. That's just true. So the sulfur didn't change. I've got +6 for my oxidation number, so that didn't change. Sulfate in general has a -2, and this still works out. It is -2. That leaves me with my lead. Right? Again, I have 2 molecules, that's why the 2 came here. But my oxidation number ends up being +2. So my lead went from +4 and from 0 to +2. So I both oxidized and reduced my lead in order to get to where I end with this equation. All right, so lead from the lead plate went from an oxidation number of 0 to an oxidation number of +2. Therefore, the lead plate was oxidized. Oxidizing means I've lost electrons. So I donated electrons, I lost electrons to this reaction. In this case, that makes it my anode, right? My anode is my lead plate, which was oxidized in this reaction, oxidized, lost an electron, well, several, lost electrons. It's my anode. The lead from the lead oxide was reduced, went from +4 down to +2. In order to do that, I had to reduce, right? So the lead from the lead oxide was reduced. Reducing means I've gained electrons. So this plate gained electrons. That makes it my cathode, okay? So for this battery that we've created, I have an anode which was oxidized. The oxidized plate is the anode. The reduced plate is my cathode. So I have both a oxidation and a reduction required in order to make a battery. Okay. All right, so I hope this was helpful, and please send me an email if you need any further assistance in this area. Thank you for watching my video. please like and subscribe. If you have any questions that I can help you out with, I'd be happy to try and answer your questions. Send me an email at morelearnmoreteach@gmail.com.